start a little more at the beginning. And like what distinguishes computer science from physics, for example. And in fact, it's the notion of event that does. If you look at a flip-flop flipping, for example, it changes from, say, 0 to 1. Well, if you're a physicist and you put an oscilloscope on that flip-flop, you'll see that, well, it's maybe not exactly 0. It's sort of close to 0, maybe wiggling a little, and then it the flip-flop will start flipping, and it'll sort of go up like this, and the voltage will come around like that, and eventually, in what to some physicists might seem like a long time, maybe a tenth of a nanosecond or so, it stabilizes to approximately a 1. Well, in computer science, what happens is we abstract that physical process of changing from 0 to 1 into a single event. That's atomic indecomposable event. And so a digital system is one in which we can view a behavior, an execution, whatever, of the system as consisting of a collection of those atomic events viewed at some level. And the atomic event may be the flipping of a flip-flop. The atomic event may be the receipt of a message. It may be the computation of that may take several microseconds or perhaps a minute. Because we're not concerned with what is happening during the actual length of time that event is occurring, because there's no interaction with what else is going on during that time, and so we pretend that event happens as an indecomposable atomic event. A representation of the system as events is an abstraction. And we make that abstraction, we consider that abstraction for a purpose. We're not creating art. We're trying to understand the systems we build. And if you're a hardware engineer, well, if you're a real hardcore, what a colleague of mine calls friend of the electron, you wouldn't consider the flipping of a flip-flop as a single event. You'd have to worry about this period of this transition period. But if you're designing hardware at a higher level, then the single event might be not the flipping of a single flip-flop, but the setting of a certain register, which is a collection of a whole bunch of circuitry. And when you're viewing it, generally it's at the software level, you're viewing it at a higher level of abstraction, where the individual events represent bigger things, such as the receipt of a message, which involves basically electrical signals that have been propagating along the wire, suddenly being received and processed, and all of this electrical stuff that I have no idea what's going on is done when somehow the operating system says, here's this message, it has just arrived. And we represent that as a single event of the arrival of a message. To say that you have a digital system or a discrete system means that you are considering its behavior as composed of discrete events. And even within the in software, for example, you can view the same thing at different levels. For example, you might say, think of at some level, represent the receipt of the message as a single event. But if you say, look at the internet, down at a different level, well, you see this message has actually been broken up into packets that are going all over the place, and the receipt of that message is actually a collection of events at the lower level. But I read the paper, and I realized that they didn't get it quite right, because the way they described their system, it was possible that a violation of causality was possible. That is to say, one event, one operation that happened before another operation would have been executed as if they had occurred in the opposite directions, opposite order. And what was going on was very obvious to me, because I understood special relativity, and I think a fairly visceral understanding of special relativity. And the thing about special relativity is that events, which are in special relativity points in space-time, are not totally ordered. There's a partial order, and the partial order is defined by the fact that by the speed of light, and one event occurs before another if that event could influence the other, and that means that it is possible for a light beam to get from where this event happened to where that event happened before, after for this event to have emitted a light beam that arrived where that other event happened before that event happened. And I realized that what was going on in the distributed system, and clearly in distributed systems everywhere, was that you had a completely analogous partial ordering of the events that happen in the distributed system, where the ordering is not by light waves that could have been sent, but messages that actually were sent. So that an event here happened before an event there. If there was some message that was sent between after this event here from here, and that arrived at that event at that place before the other event, or more generally, if there were a chain of messages, messages from here to there, and then a later message sent to there that got there, after this event and before that event. And these are not clocks keeping real time; they're just counters, but they can use them as time, and you can use them, and you can use that clock ordering to order all the events in the distributed system and get a linear ordering of them that preserved causality. The basic rule for maintaining these clocks is that first of all, whenever an event happens at a place, that local clock gets advanced, so you don't have two events at the same place happening at the same time. It's possible that two clocks read exactly the same thing, but you sort of pretend that there's a decimal point at the end containing the location that identifies the location, so it's impossible for two clocks at two different places to have exactly the same time. And then the other part of it, and the part that Johnson and Thomas missed is that when you receive a message, you have to advance your clock both later than its current value and later than, that each message has a timestamp attached containing the time at the sender that it was sent, that local time.
Right.
And when you receive a message, you have to advance your clock so it's both later than its previous value and later than the value attached to the message you've just received. So that's the whole algorithm for. The thing is, you take a partially ordered set of events, and by introducing these clocks, you totally order them. And then I realized that being able to totally order the events gave you the power to implement anything you wanted in a distributed system. That is, they were only thinking about their particular distributed database system, but I realized that having this global ordering allowed you to implement almost anything.